Hey there and welcome to the CodeWrinkles channel for this brand new video. Equality comparison seems very straightforward in C#. Like if we want to compare two objects for equality, we can use the equals method or the equals operator and we are covered. However, there's more to the story than this, and in this video I will go into some scenarios in which if we don't understand exactly how equality comparison works in C#, we can have really big performance problems with our applications. So let's dive right into it. To get started, I want to emphasize first that actually in C# we have two different concepts of equality. We have reference equality and we have structure equality or value equality. And these concepts of equality are actually applied differently depending on what types actually we want to compare for equality. So let's start first of all with the reference equality, which is fairly common because it's actually applied to all reference types. It means that to all objects or to all classes that we might define, by default, if we compare for equality, we have this concept of reference equality. And let me just briefly add here a class. For instance, we have this address class. And it's a very simple class, and we want to prove how reference equality works in this case. And we have a very basic constructor, and we have two properties like the string and the number that would belong to a certain address. Cool. Now let's, for instance, instantiate two objects of this address class. So we have address1 and address2, and I have specified here a value like for the street 5th Avenue, and for the number once I have specified 15, but then I have specified 10. Let's even make those both 15, because this actually helps us to understand exactly what this reference equality means. Now, to test this out, let me just add two other lines of code here, which are two very simple console write lines. First of all, we want to actually use this equals method, like we want address1 and we want to check if it is equal to address2, and then we want to check if the hash code of address1 is equal to the hash code of address2. And we can then run this application and we can then evaluate the result. And in this case, I assume that most of us will probably expect the result that we will get here, so it shouldn't be any surprise. However, I think that we need to explain a little bit how comes that this certain result will be displayed in the console. And in just a few seconds, we see that false and false. So this is actually what this concept of reference equality means, because here we have the instance 1 and here we have the instance 2. And as we know for reference types, is actually the value of this variable is a reference to a location in memory where this object is actually stored. So reference equality actually checks if the reference is actually the same. So it checks virtually if both of the references for address1 and address2 are pointing to the same location in memory. And in this case, since we have two different instances of this type, then it's clear that we point to different locations in memory. So even if the values here that I have provided for the street and for a number are the same, from the point of view of this reference equality, these objects are totally different. And that's actually fine. And we can actually also look into this other thing here, because right now, if we add the following lines of code, like address1 equals address2, and then we do print in the console exactly the same things again. And if we run the application, in this case, I would expect that those two should be then equal. Now, there is one other thing that I would like to briefly explain about reference equality, and in the meantime we see that it's true and true. So right now, since we have actually said address1 equals to address2, so it means that address1 right now has actually the same reference to the same object as address2. So in this case, when we check for equality, since it is a reference equality, everything works just fine. And we get the result that we expect, because right now both of the instances are actually, or both variables have the really same reference to the same object in memory. So this is actually how this works. Now, the reason why this is important is because you might work with some classes that you use from different libraries and or that might have been written by different developers, and you don't really maybe have access to the source code, or you don't really want or are able to check every time that you are actually using these equals. Now, the problem with this reference equality is that if somebody overrides this in their classes, like to implement a custom equality, in that case, when you call this equals, it kind of like will use that custom equality comparison that was implemented in that class. So this means that if you really want to make sure at a certain point in your application that you check for a reference equality, one thing that you could do here is, for instance, to be explicit about it, you can say, for instance, console.writeLine, and in this console.writeLine, you will have then, sorry for all these typos that we have here. So here we have then object, and on the object we have this reference equals, and we have to specify address 1 and address 2. And in this case, we kind of like specify explicitly that we want to check for reference equality. So we can even get rid of this object, because this method kind of like is there for each implementation of the object, like for each class. And if we run this application, we will get, in this case, the really same result. But the main difference is that in scenarios where you really want to check for reference equality and you are not sure exactly if that, well, standard or default equality implementation was overridden or not, you can then just use this reference equals method, and you are, in this case, 100% sure that you will always check for reference equality and that this is not really overridden. So this is kind of like it for the reference equality. It's really easy to grasp. And as said, it is applied to all reference types. So to all classes that we create, the default equality comparison that we have on our classes is reference equality. Now let's get to the second type of equality, which is actually very, very interesting. And here also there might be some potential problems if you are not really careful on how you use that. And this second type of equality, as mentioned, is structural equality. When it comes to structural equality, we don't really care if two instances hold the same reference to the same location in memory of those two instances, but what we do care about is the intrinsic value of those instances. And as a first go-to example in .NET and C# for structural equality are value types like structs. And let's have here a struct, which is the address. It's virtually exactly the same that we had previously, but instead of our address being a class like we had it previously, now it is a struct. And if it is a struct, we'll see that there are some very, very nice nuances and differences when it comes to comparison for equality. And here is why actually it's very important that we do in the console write line. So we check the hash code, and then we also have this equals method. Now, before we actually run the application, I would like to briefly run you through what exactly happens or how exactly structural equality is implemented in value types in C#. Now, the idea is that, as said, in structural equality, we don't care about, well, a reference or something similar to that, but we care about the values. So it means that when actually we check for equality, like we do it here, what will happen here is that on value types, there is, or the default reference equality is actually overridden. And instead of that, actually, we just compare, or C# just compares if the street is the same and if the number is the same. And it does this usually using reflection. Now, of course, there are a lot of CLR optimizations and JIT optimizations that might achieve us, or that might help us to achieve a better performance when we do equality comparison on value types. However, there might be some problems here, because the one thing to note here is that when we check for equality, as said, we compare, or .NET compares basically the values of all the fields, because each property has actually a backing field. So what it happens when we do this comparison for equality, it really checks if, for instance, the address, or if the street for this instance is exactly the same as the street of this instance, and if the number of this instance is exactly the same as the number of this instance. And if this is the case, then we can consider, or then .NET considers that we have then equality, or that those two instances are actually equal. Now, the thing is here that when we actually think about equality, there is another very important thing that comes into play, which is the GetHashCode. GetHashCode is actually a method that is really implemented once again on all types that we have in C#. It's part of the object class, but it's also overridden, for instance, as part of the override of equality in value types. And the GetHashCode, however, here performs a little bit differently than the comparison for equality, because as said, when we compare for equality, we usually check through reflection that the street is the same and that the number is the same. However, doing the same for computing the hash code will actually result in a, well, pretty bad performance. So what actually happened is that in the CLR, this is implemented, or the GetHashCode is implemented slightly differently. And the difference here is that when we do this GetHashCode, actually, what happens is that the CLR actually will look for the first field that is not null. It will compute the hash code for that field, and then it will simply return that as the return for GetHashCode. So this would mean, for instance, like we have here in the example, that we have this address A and address B, and both of these addresses actually have have the street, which is this 5th Avenue. But they have different numbers, so we would expect that they are not equal. So let's run the application and let's take a look at what we see as an output in the console, and then let's try to explain it based on what we have actually discussed so far. Because we might find here already some flags or some very important things where we actually need to be careful about when we do equality comparison on value types like structs. And we see here that for the first one, which is the GetHashCode, equals GetHashCode, we got true. But for the second one, when we check for equality, we actually got false. And that's actually already a big problem, because often what we do is that when we want to check for equality, or if we want to check two objects for equality, to make it faster and quicker, we compare, or we do this maybe also using this GetHashCode method. Now, in case of these structs, as we see, if actually the first field, like the first property that it is encountered, is actually exactly the same in two or more instances, they will actually have the same hash code, but they eventually might not be equal. So this would already be misleading, because if I would just compare in my code, or if I would just rely on the GetHashCode method to check if two structs in this case are equal, then I would be totally wrong, or my code would be totally wrong in this example. Once again, here we have just two instances, but for instance, if you have a lot of such instances that share the same address or share the same street, like here on the 5th Avenue, we might have hundreds of different numbers. So it means that we might end up having actually a bunch of different addresses that all have this 5th Avenue, but each with a different number. So if we call GetHashCode on really any of those structs, or on those instances of the struct, we would always get the same value back, or we would get that the hash code is the same. However, the equality, or those two instances, or even more instances, they are not equal, because each of them would have a different number. And this is already, as said, a very, very big problem, because here in this case, we cannot really rely on that. And let me show you some other thing is, because if we simply do here a very, very simple trick, like we just remove this property and kind of like remove it after the number, we'll see that just by kind of like switching the order of these properties, we will have a totally different outcome, which is, from my point of view, fairly crazy, because if you are not aware of that, that might cause you some real problem in the code that you write if you are using structs, because here we see that it's false and false. So it means here that, okay, this time the hash code was also not equal, so we got false, and then we got false here. So this is one result. And once again, if we just switch the properties here, like the order of the properties, then we have a totally different result for the GetHashCode. And as said, if we are not aware of this behavior, then we might actually have a lot of problems. And In this regard, actually, it's not only that we had this GetHashCode that might be a little bit misleading and that might actually bring in some bugs into our applications if we are not aware about these tiny differences that we can have depending on the order of the properties or of the fields that we have in a struct. But there are also some very heavy performance problems or issues that we can have in this case. And in fact, this is exactly what we had recently at work in a certain scenario where we used a hash set of different structs because we wanted to optimize the application, and we used headset for actually searching through well, a collection of different structs. And what it happened at a certain point is that kind of like our methods began to be very, very slow. So we need to actually look into this, and we found out actually that this type of equality comparison that we have in structs, if you don't understand it under the hood, might really bring you some big problems in your application. And let me just set up some benchmarks in this application, and then we will run this, or I will explain the benchmarks, then we'll run the benchmarks, and then we will see the difference, or if there is any difference in different types of how we do equality. So we are back and we have set everything up, and I want to briefly walk you through what we have here. So first of all, we have created two different new structs. We have this default address default struct, which is really the same that we actually used also previously, but I wanted to have it in a different class, or well, in a different struct or in a different file for the purpose of the benchmarks. And then I have another struct here, which is called address EQ override, which stands for address equality override. Now, the thing is that what I want to do here is I would like to go to the address EQ override struct, and I would like to implement the IEquatable of address EQ override. And Rider is actually very, very nice here because I can say here generate equality, and kind of like it will implement me the entire interface with how it should be implemented, like with the implementation of the equals method, the override of the object equals method, and then also with the GetHashCode that kind of like combine the two properties like the street and the number, and then they create a new hash code. Now, the idea is that for structs, and this is something that I want to emphasize. So for structs is that we need, when we have structs, to actually implement equality like IEquatable in order to make sure that we don't really get the problems that we have described earlier, and that we actually also improve the performance of our application. And that's why I have implemented equality here in this address EQ override. Now let me go here to the benchmarks to set you, or to walk you through the setup of what we actually want to benchmark. So as said in the previous example, we were doing some operations on hash sets of value types, like on structs, similar to what we have here. So we have here two different hash sets, like one for the address default, so without equality implementation, and then we have this address EQ override where we implement a custom override of equality comparison. And then here we have these params and number of elements, and we kind of like want to simulate how things will work if we have one element in the hash set, if we have 10, or if we have 1000. And what we do afterwards is we simply just generate some new address defaults here and some new address EQ overrides, and we add everything to the hash sets that we already have created. And then what we do here we have actually two methods that we want to benchmark. So one is without equality override, like for the address default, and the other one is with equality override, like on the address EQ override. And we want to compare actually how these two actually perform when head to head, like with equality comparison that we have implemented, like overridden, and without that. Cool. So now let me run the application, and then it would probably take some time until it gets finished. So I will be right back when we have the result for the benchmarks, and we will kind of like look into what this type of setup actually means in terms of performance for our applications. And here we have the results. Like we see that, okay, with equality override, or without equality override, like if we have only one in the hash set, it takes 29 nanoseconds, while with equality override, it takes just 2.9 nanoseconds. Then if we have 10 objects in the hash set, it takes without the equality override 612, and then with equality override, it's just 1.4. And we see that for 1000 records or 1000 elements in the hash set, without equality override, we have, I don't even know, 38,900 and something nanoseconds, while with equality comparison, we have 4 nanoseconds. So what we can see here is that no matter how the size actually of the hash set increases, when we have equality override, kind of like the search in the hash set performs almost the same. So it's not really exactly the same, but almost the same. But when it comes to do exactly the same thing without the override for equality comparison, we see that we have really huge differences in terms of execution time. And if we think in a real application where we might have a bunch of such hash sets that contain even more elements, then you can imagine that this could really cause in your application a bad performance problem. And the reason why we actually have this performance problem is once again the same. Well, it's the same explanation like with the GetHashCode, is because when we actually look into a hash set, that lookup is based on the hash code. And if we are in this case, like we have this address default, like we will have always the hash code, we will have basically all addresses, like all 1000 elements in our hash set will have actually exactly the same hash code. And that's a really big problem. But when we implement equality, then each will have actually a unique hash code, because the hash code will be computed as we have implemented it based on the street, but also based on the number, which actually changes everything. And to prove you that actually the problem is the hash code that is generated actually when we don't override the equality comparison, we can go here to this address default, and once again we can simply take this out from here and simply switch the order of these properties. So we actually place the number first. And what we'll do here is we'll run those exact same tests again, and then let's evaluate once again the performance of these two methods and see, first of all, we want to check if there is any performance improvement when we actually do the lookup in case that we actually don't override or that we don't implement custom equality. And the second thing that we actually want to find out is if the version with implemented equality comparison still performs better than the default. So let's just wait a few seconds and we will be right back when these benchmarks finish. And here are the new results. And we see that in this case, so we once again, we just switched the order of the properties in the default struct, and we actually have a total different outcome. However, if we look into this without equality override, we see that it's still performing worse than with equality override, but it's not that worse, so it's not that bad as it was previously. However, the conclusion here is pretty clear. When you use structs, you should definitely implement custom equality comparison by implementing that IEquatable interface, which is very, very important, and it will save you a lot of trouble with your applications. However, we are not ready yet, because in our applications, or starting with C#8, we also have this idea of records, which records are fairly interesting because they are actually classes deep down or under the hood, but are classes that kind of like implement or are implemented using structural equality. So let me go back here to the program class. Let me just also comment out this one because we don't really need it anymore. And instead, let me just add here a simple line of code like this address. Cool. So we have this here, this address record, and right now we are not using it. But once again, the idea is that for starters, this record actually is a class or a reference type, but it is implemented using actually structural equality. So we kind of like, when we check for equality two address records, we check for the street to be equal and we check for the number to be equal. So that bears the question, will the same apply as we have seen actually in structs? And the answer to this is actually no. And the reason is, and I will show you here in SharpLab. So let's move over to sharplab.io and move exactly the code that we have defined previously, like the record. Let's move it here and let's take a look actually to what is this actually lowered. But let's maybe take it out of this class and let's maybe just add it outside, because we want just to take a look at what actually happens here. So we have this address record. And what we see here is that kind of like when this code gets lowered, so our record, it's actually transformed deep down into a class. Now, the idea of the record is that it kind of like saves us from writing a lot of boilerplate code that we actually observe here when we are using sharplab.io. Because what we see is that under the hood for a record, actually, we create a class, or actually it gets lowered to a class that implements IEquatable of address record. So it's kind of like a reference type that implements a custom equality comparison. And if we take a look here, we see that for all the properties, as we know, we have a backing field. So we have a backing field for the street, and we have here a backing field for the address. And then, of course, we have these properties where we have this getter, and we have for the street also this getter and this init. And then for the number, the same. And then the address record, this is actually the constructor. And then we have here a toString. So we see that records also override the toString method that kind of like we have on objects. So we have like a very well specialized toString when we create a record, so we don't really have to care about it, but we need to be aware about this. But then actually is where actually our part is that kind of like is important for us is the not equals operator and the equals operator. However, these two kind of like also boil down to implementing custom equality, because they simply reuse what is defined in the IEquatable interface. And then we have, see here, the GetHashCode. Now, in the GetHashCode for the record, we see that actually it, it actually takes into comparison, or it takes basically both the address and it also takes the number. So like we see here, so it takes both of them, address and numbers. So this means that in case of the record, the GetHashCode, if this combination of address and number is different, then also the hash code will be different. But it also means that if the address and the numbers are exactly the same, then also the hash code will be the same. So we don't really have the problem with the hash code when we are using records like we had when we were using structs. And then if we look then down to the equals, we see that this override of the object equals method just kind of like, uses or refers to this other implementation of the equals method that we have in the IEquatable interface. And then we see here that kind of like when we do the equality comparison here, it also takes actually note of both the street, like we have here. This takes care about the street, but it then takes also into comparison also the number. So it means that when we implement equality, actually, once again, it will check both for the string, like for the street, and also for the number. So it means that kind of like this will not use the default equality that we have in reference types, but it will also not use the default equality that we have in value types like structs. So it means that here basically we have a custom equals implementation that we are spared to actually implement or write ourselves, since is actually part of the record. So once again, when we write a record, actually when we compile the code, it gets lowered to what we actually see here on the right side. So all this stuff with implementing custom equality. So that's why we don't really have these type of problems that we had on the structs when we are using records. And once again, if we think in terms of types of equality, both structs and records are actually using or are defined by structural equality. So we don't really care about what objects they reference or if they reference anything at all, but we just care that the values that we have in those instances are exactly the same when we compare for equality. And that's actually a very, very important part. Now, to wrap up, once again, let's look into the main types of equality that we have and the tricky parts in all types of equality. Like we defined that reference equality is the de facto or default implementation of equality comparison when it comes to reference types like our classes. And in this type of equality comparison, the only thing that we care about is actually that instances have or point to the same location in memory. And in that case, they are equal. Now, in this case, the only tricky part is that if we are using library code or objects or classes that we kind of like don't own directly or don't know exactly how they are implemented, they might have implemented a custom equality comparison. Like we have seen that happens, for instance, automatically for records when they get lowered to a certain class. Now, in that case, if in our applications we really care for reference equality, then we need to also make sure that we use the reference equals method to check for reference equality if we are not 100% sure if IEquatable was implemented in the class that kind of like is the object of our study, let's say, or not. So this is the trick in case of reference equality. Now, if we go to structural equality, then we have actually two different types that we have to take care about, like value types, which are structs in C# and .NET, and records. Now, we have seen that in case of structs, that is the place where we can have a lot of problems, because the equality check itself, indeed, it kind of like takes into consideration all the properties and all the fields that we have, and it checks them for equality, and it gives a correct answer. However, the implementation of the GetHashCode is different because it only looks into the first non-nullable field, and it computes the hashcode based on that non-nullable field. So as we have seen, if we have many instances actually that have for the first property or field, because we have a backing field for that as well, if they have, or we have a lot of instances that have the exact same value in that first field, then we get a lot of problems. Because first of all, well, the hash code will always be the same. So when we want to do lookups in hash tables or hash sets, as we have seen, we have a really huge performance loss. So in order to optimize, the tricky part here is when it comes to equality comparison or structural equality in structs or in value types in C#, we need actually, so once again, we need to implement custom equality comparison, implementing the IEquatable interface, and this will solve a lot of our problems. Now, the second type that we have starting with C#8 is records, and records are actually under the hood classes, as we have seen in sharplab.io, but there are classes where a lot of code or a lot of boilerplate code is already implemented, and it is implemented in a way that still we have a class, but it implements the IEquatable interface. So it means that we have a custom equality comparison that takes into consideration, once again, all the fields and all the properties on the objects. They should match in order for two objects to be considered equal, but it also implements the GetHashCode method that kind of like would also make sure that each objects, like if those two instances of two different records are kind of like different, or that there is some difference on the properties that they have, then they will also have different hash codes. But if everything is really the same when we compare to instances of records, then actually we will have always the same hash code. So this kind of are the main types of equality that we have in C#, and the tricky parts that we might encounter actually in practical day-to-day work when we are not really aware on how actually equality comparison works under the hood. And hopefully this video helped you to understand better how exactly those things are implemented and how those implementations might affect your application, so that you need to be a little bit careful about. This being said, thank you really very much for watching, and if you think that this content might be useful also for others, don't be shy and share it wherever you see fit, with your friends, with your peers, on social media, on forums, wherever you think that there is anybody that could benefit from this content. Just share it, and I'm sure that those would be really thankful to you. Also, very important, if you want to kind of like contribute to this channel, hit the thumbs up button, subscribe to this channel, of course, if you didn't do this already, and make also sure that you hit the notification bell so that you are notified whenever we have some new content here on the Code Wrinkles channel. So this being said, thank you very, very much for watching once again, and until the next time, I wish you the very best.